Hello and welcome to this short video to introduce this section, the first section of the course, which is called Don't Be Fooled by the Kernel Trick. So that's the theme of this section, the kernel trick. But what is it? Well, it's going to give us our first example so far of a non-parametric machine learning model. And we're not jumping in at the deep end. We're going to start very basic and start with a block that we're completely familiar with, a linear model. We'll then generalize this with the kernel trick to develop a new type of algorithm called Kernel Ridge Regression, which is a brilliant tool to keep in your back pocket. And along the way, we'll understand this process, this generalization process, gives us something called the kernel trick, which we can apply more generally in other situations. And on the whole, understanding what kernels are, what they mean for data sets is fundamentally important. This is my favorite section of the course, just because baked inside there is a really easy, really simple mathematical trick which can just save a lot of computational time and give you very good expressivity in machine learning models. So let's get started by having a look at some of the core objectives that we're going to run through in this section. So we want to understand, first of all, the use of non-parametric feature expansion. What do I mean by that? Features. No, let's start with features. Features are going to be the columns of our data set. They're the different variables which we want to use to predict some other target. Okay, so essentially they're our x's, and we want to predict a y, i.e., example, let's say you're trying to predict forest fires in a region. Then some of the features in your predictive data set might be the average rainfall of the region, the location of the region itself. These are all components in a great long vector, which constitutes your features, or if in other words, they're the column headings. Okay, there we go. Features, expanding them. What I mean here is by taking different combinations of them, squaring them, other nonlinear functions of them, and combinations of intercombinations between them, in order to generate new features. And non-parametric in this context simply means we don't want to touch them. We don't want the computer to have to compute many things. We want this to happen automatically. And that's where the kernel trick steps in. So that sort of leads me on to the next objective, is understanding what the kernel trick is, how it functions. That's going to play a key part of this section. And then, like I said, the hard and fast example will be developing an algorithm called Kernel Ridge Regression. This is the development of a linear model applying the kernel trick to render ourselves with Kernel Ridge Regression, which is a very powerful predictive tool. But most importantly, it's fundamentally demonstrative of this trick that we're going to introduce ourselves to. With Kernel Ridge Regression itself, we're going to look at the scikit-learn implementation of it. We'll apply it to various different data sets, most importantly some real-world data, but also some sort of graphical example data, so you can see what that looks like. And I'll take an image from that and show you just a moment, so I can paint a picture of some of these ideas. So they're the objectives. Now let's just step back 1 minute in this introduction and say, what is the trick that we're trying to describe here? I'm trying to shed some more colour on what I mean by these feature expansions. So as I said, features, they're our x's. They're the things we want to predict with, and they come to us in a vector. They come to us as a vector, which you get one component for every column name. And with the first thing you will probably do as a good practitioner in machine learning is just to check out the linear relationships between these features in your data set. Okay, so that means train a linear model. Do this first, it's a good idea. For the first point of view, you can take out that predictive tool from the data, so you can just start studying the noise, but we'll come on to that in a later video. So a linear model, it's a sum of these features, these components, multiplied by some coefficients, which I'm calling beta. So these are just scalar, these are just numbers, and the goal of the machine learning algorithm is to learn those numbers, so optimize towards them. Now, for a linear model, the solution, when you put a squared norm loss on it, is an analytic solution, which means we can just write it down. Now, the trick comes is that in the writing down of that solution, you really only need the inner product, or the scalar product, between the pairs of vectors in your data set. to write the solution down. And this is going to give us these kernels, okay? The kernel trick is then swapping those inner products for other things, but we'll get onto that later on. So, feature expansions, higher dimensional feature expansions, I mean, take those features, we've got the linear terms, we might want to square them, that's a nonlinear contribution. We might want to take trigonometric functions of them, and what I haven't written here, we might want to take interconnected functions, so for an xi, we might be wanting to multiply it by xj or xj squared, or anything you can think of. The kernel trick is, following this, we think of lots of different combinations of features, multiply them by a scalar, and we have a linear model based on these higher dimensional feature expansions. So this is roughly the structure of kernel ridge regression, except the kernel trick means we don't have to perform this expansion. We don't have to write down all the squareds and the coses or anything, or even compute them because of this trick with the inner product I was talking about. Anyway, this is meant to just wet the whistle and get you excited about the some of the lessons in this section. And I can already get the impression that a feeling of nausea coming through the lens of the camera here, but I really should emphasize equations are your best friend. Equations are going to give you the trick that we need to define good machine learning models. But if you had to choose a second best friend, I suppose you'd choose a graph. So let's try and explain that idea a bit better with a graph. Now, if we had a data set like we do here, and we're going to explore this data set, by the way, in code, so you can generate these things and solve the model on them. Here we've got a ground truth function. It's in dotted line green. It's doubly periodic. It's sort of linearly increasing. So if we plot a linear model to it, so the data's sampled noisily around it in blue dots, then the linear model is not very good. It's just trying to fit a straight line dependent on the features, which in this case, there's one feature, the x-axis, and trying to fit where the y's are with a line. Not very expressive. So we might think, can we include squares of the, and then we'd have a quadratic contribution. Could we introduce periodicity if we put in cosines and so on? No need. The kernel trick does all that for you, and you can expand the features in infinitely many dimensions and get models which fit the data in a completely flexible way where you didn't need to choose the way that the features were expanding. It's brilliant. Okay. Hopefully this is getting you excited for the module, because in your real life data sets, you probably won't be having something as straightforward as a one-dimensional problem that you can plot. You will have something where there's many dimensions, really hard to visualize. So you need flexible machine learning models that can sort of take care of that intuition for you. So let's just wrap up here with just giving you a rundown of the specific lessons coming up in the section. So first of all, a good introduction to the feature projection problem with some examples. Number two, we'll then be looking more detailed into your best friend, the equations, the mechanics of kernel ridge regression, which is the model that we're going to derive. Then, I keep mentioning this word kernels. These are going to become apparent in that lesson, but then to choose between kernels is a choice between the way that features are expanded behind the scenes. Okay, so that's very important. We're then going to look through how to implement all these ideas in code, both on graphical data and in the wild. So, after all that, there's no doubt in my mind that you will not be fooled by the kernel trick.